Okay, today we're going to take a look at solving trigonometric equations. I love this topic. Let's go ahead and get started. Students will be able to solve trig equations. Now, the reason why I love this topic is we get to use all the skills that we learned thus far in order to solve. So let's go ahead and let's take a look at our table here. We can see that we have some reciprocal properties, meaning cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, so forth, so on. We see that tangent and cotangent properties, let me draw a little line here. Tangent is sine over cosine, cotangent is cosine over sine. We have the Pythagorean properties, which are very useful. We have the cofunctions, which we've learned. We also have negative angles, which we have learned. So we're probably not going to use the Pythagorean properties in this video. I'll have a video on how to basically get one from the other. So let's go ahead and let's take a look at our first example. It says find all the solutions and radians. Okay, so we're going to treat this much like we did in Algebra 1. We're going to solve for theta. So I have 2 cosine minus radical 3 is equal to 0. First thing that I want to do is I want to basically get that radical 3 to the other side. So to do that, I'm going to play the opposite game. The opposite of negative radical 3 is a positive radical 3. And I'm going to do this to both sides of my equation. If I simplify a little bit, I get 2 cosine theta is equal to positive radical 3. I divide both sides by 2, and I'm left with cosine theta is equal to radical 3 over 2. Okay, so now we need to figure out where this is true. So what angle makes this true? A nice thing that we know already is we know the unit circle. And what we could do is basically generate a quick little sketch of the unit circle, at least the first quadrant, to figure out where this happens. So let me grab another color for my radians because it asks us to do it in radians. So pi over 6, pi over 4, pi over 3. And I'm just going to do my little order pair trick here just to save some time. I'm just going to count 1, 2, 3 down, 1, 2, 3 up, stick it all over 2, and then I can take the square roots at the top. Now, as you can see, cosine deals with the x value, sine deals with the y value. And if I grab my trusty highlighter here, I can see that the only place where cosine is radical 3 over 2 in the first quadrant is at pi over 6. So that, my friends, is your reference angle. So theta prime is equal to pi over 6. So I wish that was our only solution. It says find all the solutions in radians. So what I want to do now is use all students take calculus to figure out where else cosine is positive. So all students take calculus. So also in the fourth quadrant, remember to generate that radiant. Basically what I need to do is this. So it's a reflection and I want this radiant right here. So we learned a trick in an earlier video, the plus minus trick. Like I said, I love this topic because it uses all the information that we learned in previous videos. So what I'm going to do here is this. I'm going to say 2 pi minus pi over 6, my reference angle. And I need a least common denominator. I'm going to multiply the top and the bottom by 6. That makes 12 pi over 6 minus pi over 6, which makes 11 pi over 6. So another answer would be 11 pi over 6. Now the beauty of this is they want all the solutions. So this is the first time we've ever done this. Let me go ahead and get my black pen here, make it official. So really theta can be equal to pi over 6 and theta can be equal to 11 pi over 6. But we can also say that this will work for infinitely many solutions. And what I mean by that is this. We also have 2 pi, and you can write k or n solutions, meaning if I put in a 0, I get my reference angle, my pi over 6. If I put a 1 in, it just means I'm going my reference angle plus 360. If I put a 2 in, so forth, so on. If I put a negative value in, this accounts for all the solutions. This is my period, and this is just some variable k. So here, for my second angle, 11 pi over 6, I can also say that 2 pi times k, and add it. That'll give me all the solutions in radians. Something new. So all I did is I added plus 2 pi times some number, just to give me all the different variations. Okay, so let's go ahead and let's take a look at example 2. It says solve. We're going to do the same thing. Once again, the first part A, says all the radiant solutions. We've done that just now with example 1. We're going to try it again with example 2. Okay, so first things first, I'm going to solve. So I have 4 sine theta minus radical 3 is equal to 2 sine theta. And what I'm going to do here is I'm going to try to get all the signs together, get all the numbers on the other side. If I subtract 2 sine theta from both sides, I end up getting 2 sine theta minus radical 3 is equal to 0. It's very similar to solving for x. I'm going to add 3 to both sides, or radical 3 to both sides. I'm going to go up here, save a little bit of room. 2 sine theta is equal to radical 3, positive. Divide by 2, we get sine theta is equal to radical 3 over 2. Okay, I'm going to scroll up to our little first quadrant unit circle, and it looks like the only value for y that's radical 3 over 2 in the first quadrant is for pi over 3. So my reference angle is going to be pi over 3. So let me go here and grab my Mr. Red. So theta prime, my reference angle, is going to be pi over 3. Remember, they want all the solutions, so we also need to find out what other quadrants this is true for sine. So I'm going to use all students take calculus. Sine is also positive, radical 3 over 2, in the second quadrant. So remember our trick here. Basically what we're going to do here is plus, minus, and in terms of figuring out what that radian is in the second quadrant, I'm just going to simply say pi minus my reference angle, and so pi minus pi over 3. I need a least common denominator of 3, so I multiply 3 times the top and the bottom. I get 2 pi over 3. So I have solutions, theta is equal to pi over 3, and also theta is equal to 2 pi over 3. But remember, they want all the solutions, so plus 2 pi k plus 2 pi k. This just gives me more revolutions clockwise and counterclockwise around the unit circle. Okay, part B. So now what they want us to do is they say, okay, just give me the solutions from 0 to 2 pi. Okay, no worries. We actually found those. Remember, our reference angle is pi over 3. And we also have an answer in the second quadrant, 2 pi over 3. So that's all they want. Those are the only two that make this true. Remember, we used all students take calculus to figure out where else sine is positive. Okay, example 3, the final one that we're going to look at in this video. It says find all the radian solutions. Okay, no worries. Hopefully you're having fun. It's a nice little topic, and like I said, it uses all the information we learned before this video, which is kind of nice. Okay, first thing I'm going to do is I'm going to try to get cosine together. So I'm going to subtract cosine theta from both sides, just so I don't have to deal with a negative cosine. I'm then going to get negative 5 is equal to cosine theta. I then have still my negative 2, so I'm going to add 2 to both sides. You end up getting negative 3 is equal to cosine theta. Now I have a problem here. If you were to sketch cosine, so the period is 2 pi, take half of that, you get pi, add 0 plus pi divided by 2, you get pi over 2, add pi plus 2 pi, you get 3 pi divided by 2, and we know that we have basically at 0 the height is 1, at pi over 2 it's going to be 0, at pi it's negative 1, at 3 pi over 2 it's 0 again, and then at 2 pi it's 1. And so basically, let me go ahead and write my amplitude here. You get a sketch that looks like this. Now our y, our height, is never going to be negative 3 in this case. So this one would be no solution set. There is nothing I can put in for theta to make this true. Let's go up and see what our learning objective was and see if we met it. Students will be able to solve trig equations. I believe with a little bit of practice you're going to be excellent at this. I'll see you on the next video.